Moving forward, we're going to be talking about the two different types of encryption. The first one will be the symmetric encryption. In symmetric key encryption, or so-called symmetric cryptography, the same key is used for both encrypting and decrypting a specific message. Symmetric key ciphers are valuable because of three main reasons. The first reason is it is relatively inexpensive to produce a really strong key for these type of cryptographic ciphers. The second reason is that the keys tend to be much smaller for the level of protection they afford. And the third thing is that the algorithms are relatively inexpensive to process. So we have three main advantages here. Moving forward, we can say that implementing symmetric cryptography, particularly with hardware we're talking about, can be highly effective because you don't need experience any significant time delay as a result of encryption and decryption. So you don't experience any delays. It's pretty quick, pretty straightforward. Symmetric cryptography also provides a degree of authentication. And that's only because data encrypted with one symmetric key cannot be decrypted with any other symmetric keys. So therefore, if you know that you gave that key to a specific person, only he or she can actually decrypt it if they don't lose the key. This is the main point here. As long as the symmetric key is kept secret by the two parties using it in order to encrypt communications, each party can be sure that it's communicating with the other party, as long as the decrypted messages continue to actually make sense. Usually, with a symmetric key, you can exchange the key with another trusted participant. That's typically when you produce a unique key for each pair of participants and use it that way. You can be assured that any message that you exchange, which are encrypted in a specific key between the two participants, can only be decrypted by the other participant that has the actual key. In this way, the key must be kept secret to each participant. Very important thing, and here we see that key management comes into place. How to manage your keys properly, how to secure them, how to store them in a secure manner so no one unauthorized has actually access to them. Consequently, these keys are also referred to as secret key ciphers. If anyone else finds the key, it affects both confidentiality and authentication. An actual attacker with an unauthorized symmetric key not only can decrypt messages sent with that key, but can actually encrypt new messages and send them as if they come from one of the two parties who were originally using the key. So you see here, you have full house of goods. If you get just one key, you get the whole thing. The major drawback to secret key ciphers is actually the part of exchanging the key. That's because any exchange must retain the privacy of the key. This usually means that the secret key must be encrypted properly with a different key. The recipient must already have the key that will be needed in order to decrypt the encrypted secret key. So we get the key that is going to be used in a communication. Beforehand, we've actually exchanged another secret key with the second party and then encrypt that key with the one that was first exchanged in order to transfer it over to the second party. It's really easy when you have a physical access or just can be physically together with the second party in order to exchange those keys without using the internet or any type of communication that might be compromised. So the whole picture here can lead to a never-ending dependency on another key. So we need the key to encrypt the key, and then we need another key. So there are some advantages as well as disadvantages here. But moving forward, we'll talk a little more about the more complex type of. In this section, we're going to be focusing on asymmetric cryptography, or so-called public key cryptography. The asymmetric cryptography uses two keys, public and private, in order to encrypt and decrypt data. Those keys are simply large numbers that have been paired together but are definitely not identical. This is where the asymmetric part comes from, of course. One key in the pair can be shared with everyone. It is called the public key. Everyone knowing the public key is actually using it to encrypt a specific message sent to the other party. The other key in this pair is actually kept in secret. It is the so-called private key. Either of the two keys can be used to encrypt a message, but the thing here is that the opposite key from the one used to encrypt the message can be used to decrypt it. So we have one key that decrypts, but it cannot encrypt in a case where we have public and private key. So if you have encrypted a message using a public key, you can only decrypt it with the private. Either of the keys can be used to encrypt a message. And that means that if you encrypt it with the private, then you can decrypt it with public, which is not very secure. So in other words, it's always good to encrypt things with the public in order to decrypt them later with the private key that's not known by everyone. Many protocols like SSH, OpenPGP, SMIME, SSLTOS rely on asymmetric type of cryptography in order to encrypt and use the digital signature functions. It is also used in software programs such as web browsers, which need to establish a really secure connection over the unsecure network, like the internet, or need to validate a digital signature, for example. Encryption strength is directly tied to key size, and the fact that we can double key length, it will delivers a really significant increase in strength. Although it does impair performance, of course, but you always trade one for the other, try to find a balance point. So you trade the security for usability and vice versa. So it's good to have a really good length key, but not one that will overload and really slow down the performance. As computing power increases and more efficient factoring algorithms are discovered, the real ability to factor larger and larger numbers also increases. Here, for asymmetric encryption, in order to deliver confidentiality, integrity, authenticity, and non-repudiation, users and systems need to be certain that that public key is actually authentic, and it belongs to the person or company or just entity claimed, and that it has not been changed or tampered with or replaced, for example, by an attacker or a malicious third party. There is not a perfect solution for this public key authentication problem, really, but a public key infrastructure, or the so-called PKI, where trusted certificate authorities certify ownership of a specific key pairs and certificates, is used as the most common and actually working approach these days. Encryption products based on the PGP, for example, or the pretty good privacy model, and that includes OpenPGP, rely on a decentralized authentication model called a web of trust, which model actually relies on individual endorsements of the link between user and public key. Here we can talk a little about Diffie and Hellman. So Whitfield Diffie and Martin Hellman, which are researchers at Stanford University, first publicly proposed asymmetric encryption in their 1977 paper, The Directions in Cryptography, New Directions in Cryptography. This was the name of the paper, of the article. The concept had been independently and covertly proposed by James Alice several years before, while working for the Government Communication Headquarters, or the GCHQ, the British Intelligence and Security Organization. The asymmetric algorithm, as outlined in the Diffie-Hellman paper, uses numbers raised to specific powers in order to produce decryption keys. The RSA or Rivers-Sharim-Edelman is the most widely used asymmetric algorithm. It is embedded in the SSL-TOS protocol, which is used to provide communication security over a computer network. The RSA drives its security from an actual computational difficulty of producing large integers that are the product of two large prime numbers. The multiplication of two large prime numbers is easy, but the difficulty of determining the original numbers from the total factoring forms, that actually forms the basis of public key cryptography security. The time it takes to factor the actual product of two sufficient large primes is considered to be beyond the capabilities of most attackers these days, and that excludes nation-state actors who may have the ability and access to really sufficient computing power. The RSA keys are usually 1024 or 2048 bits long, but experts believe that the 1024-bit keys could be broken in the near future, which is why the government is taking a precaution here, and of course the industry does the same thing and are moving to a minimum key length of 2048 bits. So 2048 bits is something that we are aiming at, and all the agencies, industry is using these days, or trying to use. The elliptic curve cryptography, or the ECC, is gaining favor with many security experts as an alternative to the RSA. And this is in order to implement public key cryptography. The ECC is a public key encryption technique which is based on elliptic curve theory, which has the ability to create faster, more efficient, and smaller cryptographic keys. ECC generates key through the properties of the elliptic curve equation. In order to break ECC, one must compute an elliptic curve discrete logarithm, and it turned out that this is a significantly more difficult to execute, a really difficult problem than the factoring. As a result, ECC key size can be smaller, really smaller, significantly smaller than those which are required by the RSA, and yet deliver equivalent security with lower computing power. So really efficient here. We're talking about small little resource used, making it more suitable for example, mobile applications. We can talk a little more about digital signatures and the asymmetric cryptography. And here we can say that the digital signatures are based on the asymmetric cryptography and are meant to provide assurance of evidence to origin, identify and give an active or a live status of an electronic document, transaction, or different message, as well as acknowledging informed consent by the signer. In order to create such signature, signing software, such as for example an email program, creates a one-way hash of the electronic data to be signed. The user's private key is then used in order to encrypt the hash, returning a value that is unique to the hash data. The encrypted hash, along with other information, is then used as a hashing algorithm, and that actually forms the digital signature. The change in the data, even to a single bit, result in a different hash value. We're going to be talking into more in-depth about hashing algorithms, how to break the hash and all that in this course. So keep in mind that hashing is a huge part of the whole cryptographic and securing of data in transfer, data in rest, and so on and so forth. So here with hashing algorithms, we can say that if the decrypted hash matches a second computed hash of the same data, that really proves that the data hasn't changed since it was first signed. If the two hashes don't match, the data has either been tampered or the signature was created with a private key that doesn't correspond to the public key presented by the signer. And that would indicate a failure of authentication. A digital signature also makes it difficult for the signing party to deny having signed something. The property of non-repudiation, very important thing these days and really important part of the security in general. If a signing party denies a valid digital signature, their private key has either been compromised or they're lying. In many countries, and that also includes United States, digital signature has the same legal weight as the more traditional forms of signatures. So keep that in mind and make sure to understand the whole concept of digital signature as it is used widely these days, and you can find that while just browsing internet through your web browser. Start looking and keep attention to small details, small different messages that pops up. Try to see where the certificates on your browser are stored at. What is signature third party that would actually verify your signature, so a signing authority and all that. It's really something to look at and understand that will help you in your future as a IT cybersecurity expert. As a conclusion, let's look at the Main differences between symmetric and asymmetric encryption. The symmetric encryption uses a key that needs to be shared among the people who need to receive the actual message. On the other hand, asymmetrical encryption uses a pair of public key and a private key in order to encrypt and decrypt messages while communicating. The symmetric encryption is an old technique, while asymmetric encryption is definitely something new. Asymmetric encryption was introduced to complement the inherent problem of the need to share the key that is actually the fundamental thing in symmetric encryption model. And though eliminating the need to share the key by using a pair of public-private keys. And lastly, asymmetric encryption takes relatively more time than the symmetric encryption. To conclude, we can say that when it comes to encryption, the latest schemes or the latest algorithms may necessarily be the best fit for you. You should always use the encryption algorithm that is right for the task at hand. In fact, as cryptography takes a new route, new algorithms are being developed in a bid to catch up with the malicious attackers worldwide. So they're really advanced, they're moving one step ahead, always having the resource, the knowledge, and the mindset to break things and find the smallest vulnerability or hole into a security model of an algorithm or a whole system. So hackers are actually bound to make it tough for security experts in the coming years, and thus expect more and more from the cryptographic community, as this is a dynamic world, dynamic environment, and the need to create newer and more secure algorithms is never stopping. Thanks for watching, guys. Stay tuned with our next video.